Okay, so continuing our journey with the origins of electronegativity. Now remember what I said just a moment ago, that electronegativity is a calculated value which has this nice convenient range of 0.73 to 4, a bit like a GPA, right? Okay, and that convenience comes from the fact that other actual experimental numbers are put into this equation, and then it's fiddled around so nice numbers pop out. Okay, now the things you put in there, and we're going to look at atomic size and first ionization, they follow the same trend as electronegativity, a diagonal trend. However, one of them is low to high, just like electronegativity, and one actually, although it's diagonal, starts high and then goes low. So they're always diagonal, these trends. Okay, one is proportional, low here, high here, just like electronegativity, and then one is switched, if you like. Okay, so we'll see always a diagonal trend, and the question is, when we look at these two things, which is low down here, which is high up here, and then which is high down here, which is low up here. All right, now it's actually pretty common sense, to be honest. All right, so when we look at radius, or the size of an atom, okay, what do we expect to see? Now, on a separate piece of paper, I really kind of advise you to do this, right? So what I'm going to do, I'm going to kind of look across row 1. So here's row 2. So here's lithium, all right? And I'm going to run all the way across to neon. So we're going to look at across a row how size varies, and then we're also going to look down a column how size varies. If I go all the way down to the bottom, maybe 7 layers, cesium or something, and I can keep going, kind of. There's going to be 1 electron on the outside though. I won't fill in the stuff underneath, right? Maybe I'll put cesium there. Okay, there we go. Kind of hard to see, there it is. Oh, just about get it on the screen, right? So, question, and I'll kind of talk you through as we go, all right? So, how do trends of radius or size change across a row in the periodic table and down a column? Down a column is actually the easier one, all right? Let's think about that just for a second, all right? So, if I'm thinking about the size of atoms as I go down a column, are they getting bigger or smaller as I go down? If you said bigger, you'd be right, obviously, because every time I go down one, I add a layer of electrons in the core, don't I? So, larger going down. So atoms always get larger going down, okay, because every time you add a layer, you're further out, okay? So we'll start with actually the second point here. Down a column, atoms become larger due to more layers of electrons or shells. So that's a nice easy concept. As you go down a column, atoms get bigger because every time you go down one layer, every time you go down one row, if you like, you add one shell of electrons which are further out, makes the atom bigger. Fair enough, right? Fair enough. So that's that concept. That's a nice, easy concept, right? But what about across a row here? Now this is where it gets kind of interesting, okay? How does the size vary across here? Now, if you think about this with a certain degree of kind of everyday common sense, you think, well, I'm putting more electrons around there, they need more space maybe, so maybe the atom gets bigger. That would be your first kind of guess, perhaps, right? And the first guess is absolutely wrong, it turns out. Because if you think about it, this is one of my favorite analogies, right? So think about when you go to the, the fairground or the carnival or something, you go on the carousel and you have that inner ring of animals, next ring of animals, next ring of animals. I really like riding the giraffe, don't ask me why, right? Okay. But it doesn't matter if there's a person sitting on the giraffe or not, right? It doesn't matter if there's an electron in the hole or not. It doesn't alter how far out those electrons or animals actually are with their riders, okay? So it turns out that this atom should be exactly the same size as this atom because we're adding riders to animals in the same ring, right? Okay, so it doesn't matter, right? It doesn't matter if I got one on the outside, they're all in the same ring, all the same distance from the nucleus. and we're good. But that's not true either, it turns out. Okay, and there's a very, very weird and unusual way to explain this, and I'll try and do this for you, right? It's because of a fact or an effect we call shielding, okay? Now, shielding is all about working out the effective nuclear charge, and that has the symbol ZF, right? Now, think about this. If I look at, and the classic example is the first row here. If I look at lithium, lithium is element number 3, so I think about an attractive +3 nucleus, fair enough. But then I've got 2 electrons, and I'm going to do kind of a mixed model here. So if I do kind of my wave diagram instead of my dots, I've got 2 electrons between the nucleus and that outside electron, don't I? Okay, so when this outside electron, which is the valence electron, which is the important electron, looks in, what does it see? Well, that's what it has, its effective nuclear charge, right? What does it see? Well, through the clouds, it kind of sees the +3 nucleus, right? So it sees the nuclear charge, which it's attracted to. However, there's 2 electrons in the way, which are minus, aren't they? And those are called shielding or screening electrons. So you subtract, like a tax rate, you subtract 2 electrons, which is a -2, getting in the way of the +3, and you're left with an effective nuclear charge of +1. And it turns out, when you do the math, everything in column 1 has an effective charge of +1. If you did that math again, everything in column 2 would have an effective charge of +2, etc., all the way across, right? So if neon's in column 8, what's its effective nuclear charge? If you said 8, you'd be right. Let's work it out. So let's do that little map again, right? So I'll take my neon. Neon is element number 10. It's got a +10 nucleus. Then it has 2 in the way, right? And then I've got 8 electrons on the outside. It doesn't matter how many electrons are on the outside because they're all looking in, right? They don't see each other, they just look into the center. There's 2 in the way, it doesn't matter where you are, there's always going to be 2 in the way. So the effective nuclear charge is the nuclear charge 10 minus the number in the way, which is 8. Okay, so column 8, effective nuclear charge. Column 1, +1, effective nuclear charge, and 2, 3, 4, 5, 6, 7 in between. Okay, so those are 2 extremes. So what have we got? As we go across any row in the periodic table, the attractive pull of the nucleus increases. If you think about it, we're adding a proton for every element we jump over, so that makes the nucleus more attractive. But we've got the same 2 electrons screening that nucleus, getting in the way, right? So the amount of tax stays the same, but the income, if you like, goes up. So the nucleus is more and more attractive. Now think about the effects of that. If these electrons see a +8 nucleus rather than this one that sees a +1, which are they more attracted to? They're more attracted to the +8, aren't they? So they actually squish in just a little bit. So across any row, we see this very minor contraction in size. So across a row, atoms actually get smaller. Now that's counterintuitive, isn't it? Atoms get smaller across a row, but it's true. So let's write that down. Across any row, atoms become smaller across a row due to increased ZEF. Okay, effective nuclear charge. And you may want to kind of staple this or include this in your note packet so you understand that concept, okay? Think about that, makes sense. Why does group 1 make a +1? Because it's really easy to get that electron out of there because it's only being held by a +1 effective nuclear charge. Why do things on the right make minus ions? Why do they steal electrons? Because they've got a really strong effective nuclear charge pulling electrons in. So that kind of makes sense. All right, now, if we combine these 2 effects, okay, what do we see about the atomic radius trend? Well, is it diagonal small to big or big to small, right? Let's look at this. So where's the largest atom in nature, top or bottom? Well, from our first trend, it's bottom, right? Where's the biggest, left or right? It's going to be left. So the biggest atoms are on the left at the bottom. So this guy here is the largest. All right. So bottom left is largest. Makes sense, right? Where's the smallest? Well, it's going to be at the top, and it's going to be to the right, which is actually, in nature, helium is the smallest atom. Okay, that's the smallest. Okay, so our trend, yes, it is diagonal. But for radius, it's actually the largest atom here. It's the smallest atom here. If you want to remember something, the radius is the only one that goes big to small. Everything else is large to small. Sorry, it goes big to small. All other trends are small to high. Okay, so largest radius is lowest electronegativity. Okay, when we do first ionization, lowest first ionization is highest radius. Okay, all right. So that explains that kind of weird concept. We can explain that size thing with screening, okay, across a row. Now, to show I'm not lying, here is the actual data, okay? So if we look, it's the same kind of columns and rows I chose just because it's a good example. So we go down a column, they get smaller, these are picometers, okay? And across a row they get, down a column they get bigger. Make sure we get this right. Down a column they get bigger, and it's true for any column, they all get bigger as you go down. Across any row they get smaller as you go across and increase that effective nuclear charge. There it is. Now here you may say to yourself, well, what's up here? Nitrogen's weird. This is actually the correct number, so that's actually 75. Okay, so it is actually a true trend. Okay, and if we look at the diagonal then, hey, it gets bigger going down, smaller going across. Bottom left is the biggest, top right is the smallest, and that's the periodic table in terms of radius. Okay, now if you just remember that, okay, so the questions we can ask are actually pretty simple. We just ask you to put atoms in order of size, right? Okay, so always bottom left or top right. Remind yourself, bottom left is big, top right is small. Okay, now what we like to do is ask questions like this. Okay, so we give you a few atoms. I'm going to give you 3 to start. It might be 4 or 5 later on, right? So arrange these atoms in order of increasing size. Right now, careful, careful, careful. If I'm going to arrange them in a list in order of increasing size, do I start small and go big, or start big and go small? Increasing, I start small and go big. That's what I'm going to do. All right, so if I think about it, the smallest is going to be, remember our trend, top right, right? So that's going to be top right. And the biggest is going to be bottom left. Okay, now here's the thing. This is my little trick, right? What I like to do, sodium, beryllium, magnesium, right? It's actually, I've chosen these on purpose. They can be more spread out, all right? But they're kind of in a triangle, aren't they? A nice, easy triangle, which allows me to say, hey, who's bottom left, biggest, who's top right, smallest, and then kind of who's in the middle, okay? So draw yourself a little map. Draw yourself a little map of the relative positions. Doesn't matter if they're spread out, doesn't matter if they're close. Just, hey, who's left, who's right, who's up, who's down, right? Make yourself a little map like that, okay? So I'll make the map. Okay, so I've just translated that part of the periodic table over. All right. Now remember, I say to myself, well, the biggest atom in nature is bottom left. And the smallest is top right. And then I say, well, where do they fall on that diagonal line? I want the smallest first, right? Smallest is top right, that's beryllium. I like to do bookends. Who's bottom left? Sodium. Who's in the middle then? Magnesium. It's where it falls on that diagonal. Okay, where it falls on that diagonal. All right. So there you go. Nice easy points on the test. Remember the trick. If they want increasing, small first, big second, or sorry, small first, biggest last. Smallest is top right, biggest is bottom left. Put them on a diagonal line. You're good. All right. The second and final trend we'll look at is first ionization energy. Now, kind of an easy concept actually. If we think about ionization energy first, right? What is ionization? Well, you get a metal and you kind of pluck off an electron. You pull an electron away from an atom. It can be a metal, it can be a non-metal, it doesn't matter what it is. You can pluck electrons off any atom. I don't want to go into too much nitty-gritty detail here, but you can actually have a machine that does this. So you have two metal plates with a very small gap. You put the atoms of choice in between, right? And then you put like a really big variable voltage across there, right? Okay, and you change the voltage, and voltage is just like, you know, if you had a ball on a plank and you just raise the plank, right? Eventually the ball would start rolling because that's kind of applying potential energy, right? So what you do is you do the gradient, or the slope is the voltage, right? So you kind of keep ramping the voltage, and eventually electrons will be ripped off these atoms, okay? And you can do some math and figure out how much energy it costs to rip off an electron from a mole of atoms. That's called the ionization energy, all right? But if you think about it, well, I tell you this, hydrogen has only one ionization energy. Helium has two ionization energies. Lithium has three ionization energies, because I can sequentially pull them off there, right? I can pull them off one at a time, yeah? But we want something to compare to. We want to be consistent when we compare one atom against another. Well, it turns out every atom in nature has at least one electron, even hydrogen, right? So we always compare the first ionization energy between atoms, because everybody's got at least one electron, right? Okay, so the first ionization then is defined as the energy required and it's always in kilojoules per mole. So take a mole of atoms, how many kilojoules to pull off one electron from each atom, or a mole of electrons, okay? And you know, they're always in a gas phase. Okay, so if I do a little kind of balanced equation for that, so I take my sodium, I pull off an electron, I'm left with a sodium plus, and we say I1, first ionization energy, and that's actually a small value, right? That's actually in the big scheme of things, that's a small value, right? Okay, only 496 kilojoules per mole. If I do a dot diagram, sodium's number 11, right? And we'll do the effective nuclear charge just to show it does work for other elements in the same column. We saw for lithium it was a +1 effective nuclear charge, right? Okay, so it turns into that electron is removed, right? And we're left with that and an electron. There it is, right? Okay, now if you think, sodium is element number 11, so it's 11 electrons, one on the outside. It's these two full layers, 2 in the first, 8 in the second, so its effective nuclear charge is 11 minus 10, which equals +1. Fantastic. So that electron is 3 layers out, so it's far from the nucleus, so it's kind of easy to pull off because it's further away. Think of a satellite, you know, in orbit around the Earth. The further out it is, the less strongly it's held. But it's only held by a +1 charge anyway, so that's very easy to remove. Okay. There we go. So that's why that's quote-unquote a small number. Okay. So the question, how do first ionization trends vary across a row and down a column? And we combine the sideways and the up and down, and we get the diagonal, right? So again, and I'll go back to my little example here, and we just kind of said it actually. Okay. So as I go down a column, so everything in column 1 has the same effective nuclear charge. Everything in column 2 has the same effective nuclear charge, +1, +2, right? So down a column, the attractiveness of the nucleus is the same, right? No effect. Okay, so the attractiveness of the nucleus down any column is the same for every member of that column. Group 1 is attracted to a +1 nucleus effective, right? However, what does change? Well, as we saw in the last example with radius, as you go down, there's more and more layers, right? So that electron is further out. Okay, now we just mentioned it. Hey, what's easier to remove? A satellite in a high orbit where it's not feeling as much gravity as one in a low orbit? Well, it's the high orbit, right? So down a column, because they are further out, down a column, therefore larger distance. They're further out from the nucleus, it's a larger distance, it's less strongly held. Now that's the key, right? If the electrons, the valence electron I should say, it's way out there, right? So, you know, for cesium in row 7, it's in the 7th layer, right? So 7 layers out. it's real far from the nucleus, right? The nucleus is a effective +1 for everything in the same column, so that doesn't change anything, but it's further out, so it's going to be less strongly held if it's further out. If it's less strongly held, it's easy to remove. So as we go down a column, if we think about it, the first ionization gets lower. Okay, as we go down a column, first ionization gets lower because electrons are easier to remove. So if I change my diagram here, largest radius, smallest first ionization. Smallest first ionization. All right, so as we go down a column, easier to remove electrons, therefore, lower first ionization. Now, fair enough. Now, as we go across a row, yes, they shrink a little bit. We mentioned that already, okay? But that's not the 300-pound gorilla in the room. It's not. This size and this size are very close. Yeah, there's a slight contraction. But what's really going on? What's the man behind the curtain? The man behind the curtain is effective nuclear charge. It's got 8 times bigger as we progress across any row, right? So slightly smaller radius as we go across. But if we think about it, as we go across, effective nuclear charge increases. That's important, right? So across a row, effective nuclear charge increases 1 through 8. Column 1, the nucleus has an attractive force of +1, if you like, and column 8 has an attractive force of +8. So if you think about it, are the electrons being held more or less tightly? Well, the radius isn't a deal, right? Because this is so much of a bigger effect, right? So as we go across, electrons are held more strongly because the +8 holds or attracts electrons better than the +1, doesn't it, right? Therefore, harder to remove as we go across. Does it take more or less energy to remove them? Well, they're harder, so it's more. So first IE increases. So across any row, across a row it increases, down a column it reduces. So if we think about that, where's the lowest? Well, it's going to be on the left because it increases left to right, so on the left is the low. Okay, top or bottom? Bottom's the biggest, so it's going to be lowest. So the lowest value in nature for first ionization is bottom left, highest is top right. So it's the same trend as electronegativity. Same trend as electronegativity. Bottom left is low, top right is high. Okay, if we go back to our map, if I can find the thing. I know it's in here somewhere. There it is. So, first ionization and electronegativity are lowest, bottom left, highest, top right. Switch it for radius. Highest radius, bottom left, smallest radius, top right. So the odd one out is radius. We said that already. Okay. So now you know the kind of answer, so to speak, right? Bottom left is low, top right is high. Okay. Now, good news is, or interesting news I should say, that because we're just removing electrons from atoms, it doesn't matter what atom. So actually the highest in nature, okay, it's a bottom left to top right trend, just like electronegativity, but the noble gases are included. Now, important distinction, electronegativity only applies to things that can make bonds, right? So, you know, fluorine onto the left, right? If I just got some atoms, you know, in that machine, doesn't matter what the atoms are, I can use the noble gases. So the thing at the top right is actually helium. That has the highest first ionization, followed by neon, followed by fluorine. So it's that same kind of geography map we had before with electronegativity, but now it's the first ionization and it includes everything. Okay, this is just a kind of a 2D equivalent. Okay, so I want you to try this one, right? Okay, let's read the question. And then go for it, right? So, arrange the following atoms in order of increasing first ionization. So it's going to be small to large, right? Okay, we remember that the smallest is bottom left and the largest is top right. Okay, so we're going to make our little map of the periodic table, okay, relative map of where these things are relative to each other, then just draw that diagonal line. Okay, so try it. I'll catch you up. All right. So this is the one you'd have on a test. All right, so if I look at those atoms, I've got sodium, cesium, fluorine, carbon. So sodium, cesium, carbon, fluorine. There's my, oh, move it up. There's my relative arrangement, right? That's, you know, that's not how the spacing is in the periodic table, but I'm not worried about the actual spacing. I'm worried about the regular spacing. All I need to know is who's up, who's down, who's top, who's bottom, who's left, who's right, that kind of thing, right? So there it is, okay? Draw that diagonal line, okay? So I want the smallest first ionization energy. That's going to be bottom left. Cesium, yeah, cesium makes ions really easily, doesn't it, right? So cesium is the lowest. Who's top right? Well, fluorine, that's the highest, right? Then carbon and nitrogen. In terms of where they fall on that diagonal, sodium, carbon. There you go, that's my list. All right, and you can choose any 3, 4, 5, you know, however many atoms you like. Just put them in that local map, draw a diagonal line. Remember, bottom left is small, top right is high for electronegativity and first ionization, reverse for radius, as we saw in the last example. Okay, that is the end of the packet. Now that means we have one more packet to go, okay, which is, what's the name of that one? That is, what was it? I can't remember. It's been a long day. All right. Anyway, the last packet is the last. The next packet is the last packet. So once we've done that, you'll be in good shape to take your test. Okay. So I want you to try and finish the packets as soon as you can, and then start kind of practicing questions ready for your test. And remember, I'm only going to test stuff essentially which would be on the second midterm. Okay. So none of the stuff we've already tested on the first midterm. Okay. Hopefully that makes sense. I'll put all this up. Any questions in a discussion? As normal. Okay.